This Module 5 video is on conjugate or 1,4 addition. If you have a ketone that has a double bond next to it, that double bond can be labeled alpha and beta positions, the carbons of that double bond. And so we call this an alpha beta unsaturated ketone. The beta position is subject to nucleophilic attack. The reason for this can partly be explained by inductive effects. And so what we see here is the electronegative oxygen withdrawing electron density away from the carbonyl carbon. As long as you have an unbroken string of pi bonds, that effect can be propagated so that you have a delta minus and delta plus on that alpha beta unsaturated part of the molecule. And so a nucleophile can come in to the electropositive delta plus beta carbon. Even in NMR we can see effects like this, where the further proton, the beta proton, is more deshielded than the alpha proton at 5.93. Remember that shielding is due to electrons, and so if the alpha position is delta minus, it has more electron density around it and is therefore more shielded at that position, while the beta position is less shielded. It's even more obvious in the carbon NMR, where the ketone occurs at 188 ppm in this case. That's because of the unsaturation next to it, actually, where ketones are normally at 200 ppm. We have a shielded, alpha position and a deshielded beta position in the carbon NMR. So the beta position is subject to nucleophilic attack. We call that conjugate addition. If you have a nucleophile coming in like this, generic nucleophile, forming a bond to the beta carbon, it will displace these electrons up and further displace these electrons up toward the electronegative oxygen. In fact, you have an intermediate that's called an enolate ion, a very important type of ion in organic chemistry. At this point, you can have protonation occur, as we've seen, where electrons move in this manner, abstracting a proton from a proton source, and you get the ketone up here and a new bond to the nucleophile at the beta position. So the net reaction is actually a nucleophilic addition to a carbon that's 2 carbons away from the carbonyl carbon itself. As you've seen in the units of this course, we've generally progressed with the additions of different types of nucleophiles to carbonyls. And so we're going to follow that same pattern here. With hydrides, remember, lithium aluminum hydride or sodium borohydride are sources of H- anion. This can go via conjugate addition here, or alternatively, you could think about it going directly to the carbon of the carbonyl carbon. In fact, what we end up with as a result of this mixture would be 91% direct addition to the carbonyl. Notice that this proton has added and the carbonyl oxygen has protonated, while we only get about 2% of conjugate addition. This is the conjugate addition product that results from 2 times a 2-time addition of the hydride. So it's a little surprising maybe that, or maybe not, that the proton of the hydride attacks directly to the carbonyl carbon with lithium aluminum hydride, a strong source of hydride nucleophile. With sodium borohydride, it's a little bit more mixed, 53% addition directly to the carbonyl carbon, as opposed to 37% conjugate addition, again, 2 additions of the hydride. And just for completeness, let's take a look at this mechanism. So you have the nucleophile coming in via conjugate addition, arrow pushing as we've seen, protonation as we've seen, leading to this ketone here. Another hydride can come in. It's hard to control a second one coming in the course of some of these reactions. So that was this addition of hydrogen, further protonation, and you get the final product here, reflected over here and here. So there's not a lot of control for hydrides, although there's a difference between lithium aluminum hydride and sodium borohydride. With oxygen and nitrogen nucleophiles, we have straightforward electron arrow pushing of this same type, conjugate addition. We have our enolate ion here. We have protonation taking place here. We end up with conjugate addition with the new bond to an oxygen. Now we've created basically an ether here. And note that this is a chiral center. And so likely you will have a 1-to-1 racemic mixture of enantiomers at that position. Here's a nitrogen nucleophile. Can come around and do the same thing. Conjugate addition, standard arrow pushing. We can have a deprotonation to regain an amine at that position, followed by a protonation, or happening at the same time maybe even, of that oxygen, followed by tautomerization to get to the ketone. Visualize an intermediate where this becomes an alcohol, and then that's an enol that can tautomerize, that will tautomerize readily to the ketone. So you can do it in both ways, and we've seen that before. There's our new bond from a nitrogen nucleophile. With carbon nucleophiles, like our simplest original carbon nucleophile, the nitrile group, or cyanide ion, cyanoion, not sure. Nucleophilic attack, conjugate addition, kick electrons up. Here's our intermediate, enolate, electrons down, protonation. You end up with the ketone here. And we have our new bond to the nitrile, new carbon-carbon bond at that position. And again, chiral center, 1-to-1 racemic mixture. With Grignard reagents, a much more important carbon nucleophile, and in fact with organolithium reagents as well, you can easily see the Grignard reagent as a carbon nucleophile reacting in this way, adding directly to the carbonyl carbon, or via conjugate addition. Call that 1 and 2, products 1 and 2, via the same mechanisms we've already seen. In fact, the ratios of these products, 41% addition directly to the carbonyl carbon, 39% addition to the beta carbon, making this new bond or this new bond, one or the other. So pretty much an even mix. And by the way, any leftover percentages above and at this point are likely, just loss of yield, side reactions maybe, who knows. And so because carbon nucleophiles like Grignard and organolithium reagents don't actually give one or the other with great preference, it was important to develop other reagents to give better regioselectivity. And we've seen this over and over again in organic, where a more complex reagent is needed to give more specificity, whether it's regio or stereospecificity. And so lithium dialkyl cuprates to the rescue, also known as Gilman reagents. This is a copper lithium reagent that has two alkyl groups attached to it, if you notice here, that can deliver the equivalent of a methyl anion in this case. And so we use that in the first example here, where this methyl anion will go with high selectivity to the beta carbon, kicking these electrons up, kick these electrons up, protonation and so forth, 86% conjugate addition. That's pretty high specificity, creating this new carbon-carbon bond. This, what we would call an allyl group, but more importantly, a carbon nucleophile, and it's even got an alkene functional group within it, going directly here by conjugate addition, kicking these electrons up, and that takes place also with high selectivity, although I don't have the number exactly for that one. If you look at the product, it is chiral at this position, and you might expect, therefore, that you would have maybe predominantly more of this first one due to the steric effects of the methyl group adjacent here. So maybe not a whole lot more, but some more of this one rather than this one. I don't have the proportions, however. So conjugate addition using lithium dialkyl cuprates. Synthetic chemists often talk about these kind of things as hard or soft. Hard nucleophiles or soft nucleophiles. Part of the explanation for some of this behavior is that hard nucleophiles, they sort of go driving straight in for the main thing, the carbonyl carbon. Whereas a softer nucleophile can sort of go into this remote site at the beta position, which is less electropositive, but probably more accessible. So hard nucleophiles tend to be smaller, more strongly charged. Softer nucleophiles might be less charged or not even charged at all, just electrons, and maybe larger, so they can't get into where the carbonyl carbon is. So there is an entire lingo around hard and soft acids, bases. Really what they're talking about is Lewis acids and bases in explaining things like this. And just for completeness, although I'm not requiring this, for example, on the exam, lithium dialkyl cuprates are prepared in this way, where you start with an alkyl halide and you add lithium, and it sort of divides the alkyl halide up into two parts, the lithium, organolithium, and the lithium bromide. The organolithium can react with copper iodide, and the copper does sort of what magnesium does in Grignard reagents, just sort of inserts in there. You have to have two of these alkyl lithiums to create one lithium dialkyl cuprate. And so this is, of course, able to deliver a carbanion equivalent as a, I guess you would say at this point, a softer carbanion equivalent, a softer nucleophile.